So, central to the study of emotions is what we now know as the limbic system, and you should read that paper on the limbic system. That covers a lot of the major components of it that are up here. Some of these you should be familiar with at this point. Anterior and posterior cingulate cortex, for example, nucleus accumbens, hypothalamus, orbitofrontal cortex, which from, if you read the paper, is sort of a new addition to this. So bits and pieces of different parts of the brain have been added into the limbic system as our understanding of this system has evolved. So just, be aware of the circuitry, understand some of these brain areas, and as we go through this, we will talk more about some than others, okay? All right, where are we at here? Okay, so what is fear? We need a definition, and I was going to have you read this paper until I looked at it more carefully and thought, oh no, that's way too much. We will talk about it. I will present this in class on Thursday, either in class or, probably in class on Thursday. And this is sort of a good definition of fear. It's a feeling that arises when we experience an impending threat to our survival. And the paper that you'll be reading for class on Tuesday does get at this concept of a feeling. When people first started looking at emotions early on, no one wanted to talk about feelings because that wasn't very scientific. Psychologists at the time in the 60s, 70s did not want to talk about feelings, but now we accept this is something that you feel, okay? The other thing is that it's a combined behavioral and physiological response elicited by that overt threat or signal of potential threat. So what we have is a feeling. All of this is due to an impending threat to our survival or a potential threat, either overt or potential. So a threat to our survival. We see behavior, often that is avoidance. We see a physiological response, which is increased blood pressure, increased heart rate, things like that. And there's also a cognitive component as well. That's also important, so pulling it all together. Okay, and this seems a little bit kind of familiar with when we talked about the happy brain. So a lot of this it's the same idea. There's a behavior, there's the body, the physiological response, there's a cognitive component, there's this feeling of how it's all getting put together, okay? So there are different types of fear. We're going to get to this one later. And innate fear, it's activated by intrinsically threatening stimuli. So when we talk about this with rats, it's going to be the smell of a cat, the smell of a predator. And we'll also talk about innate fears in humans. So this is something you don't have to learn. It's intrinsically threatening. You kind of come this way. There's learned fears, and that's what we're going to talk about first, because this is where most of the basic fundamental research was done, was pairing up previously neutral stimuli with something that is threatening. Generally, it's a shock. Okay? And there are specific fears: fear of pain, fear of predation, and fear of aggression. Today, we're just going to focus on the fear of pain. This is related to more of the learned fears. So you're fearing that you're about to get hurt. And then we'll talk more about fear of predation on Thursday. And then when we talk about these many pathways to fear, we'll also introduce the fear of aggression, but in a very cursory manner. Okay, so first of all, sorry, poor Ron Weasley. Foot shock, fear of pain, foot shock, and classical conditioning. This is something you probably encountered in Psych 101. If you had any kind of introductory psychology course, whether it be here, whether it be, say, AP Psych, whether it's a psychology class in high school, I'm almost fairly certain you talked about classical conditioning, and we just have a different way of thinking about it, okay? So here's the general idea. There's a couple ways you can do this. You put a rat or a mouse in a box. There's an electrified grid here. Here's our little scared rat, going to be scared rat. Now, you can do it just by the context. And when I say context, I mean the shape of the cage, the box, all of this. Animal looks around, takes it all in. That is the context. For you, for example, it might be wherever you're sitting right now. If you're sitting in your room, if you're sitting wherever, that is the context in which you are. And if somebody were to shock you right now, that would be the context that you might pair with the shock. When you then do this later on, you bring the animal back into that context without the shock. It now becomes a conditioned stimulus and leads to a conditioned response, which is fear. And in a moment, we'll talk about how that response appears. You could also do a very specific thing, just a tone. You could turn on a tone. The tone precedes a shock, same thing. Next time, you could take the rat, put him in a totally different context, different chamber, different cage. Turn on that tone, it's going to also produce conditioned fear. That's the conditioned response. So that's the basic model we'll be talking about. This is looking at, say, blood pressure. In this case, this is something that rodents do when they can't escape. It's called freezing. It's a freezing response. And you may have heard about this with fear, also related to trauma. So there's the fight or flight is the one you normally hear about. So generally, the first response somebody does when presented with a fearful stimulus is you try to get away. That's flight. If that doesn't happen, you can't get away, then often you try to fight to protect yourself from the threat. And then if that doesn't work, then you freeze. And a rodent freezes, sort of hoping that whoever's out there is going to not see them. So this is just a tone by itself, okay? Not going to do anything. Blood pressure's here. They're not going to freeze because tone means nothing, but they electrify the grid. Tone is on. The grid is turned on. The rat is being shocked. You see blood pressure goes up. You see freezing going up because it can't get away. And then later on, maybe a day later, you bring them back and you turn on the tone, and they're going to show the same response as they did when they were shocked. You see increased blood pressure, increased freezing. So the work that we are going to look at, Ledoux's work, is going to focus largely on the freezing response. Okay, so let me just introduce you to the basic model that was worked out by Ledoux's lab, and then we'll probably continue that into the third presentation. Okay, here's what I just showed you. Here we have the tone by itself. It's neutral. Nothing's going on. Pair up the tone with a shock. I'm afraid. And then just present the tone. I'm afraid. So bigger the values, more fear. And this is a different representation of what that little chapter that you're reading for today talks about, the low road and the high road. So the low road is much faster. And what the low road does is everything comes in through whatever the sensory organ is. If it's vision, if it's auditory, it comes in, goes to the thalamus, and then it branches off. It splits off into two roads. The high road is going to go up into the sensory cortex. Now, this takes a little bit longer to get here. Between the thalamus to get to the amygdala, which is here, doesn't take as long. So this is the immediate response that you get. It goes initially into the lateral nucleus of the amygdala. From there, goes through the basolateral, the accessoral basal nucleus, but then goes to the central nucleus, where traditionally the central nucleus is viewed as the output of the amygdala complex. So this is a whole complex. It's made up of different nuclear groups. Lateral nucleus tends to be the input, and the central nucleus tends to be the output. From here, that information goes to a region called the central gray or periaqueductal gray, which leads to the behavior. We have the lateral hypothalamus, which leads to some of the autonomic responses. That is the increased blood pressure, the heart rate, and so on. And then we also have a hormonal response. This is a region called the bed nucleus of the stria terminalis, or BNST, and that then also goes to the hypothalamus as well, and leads to some of the hormonal responses. While all this is happening, this information is also going up into the cortex, where it can be more closely evaluated. Is it really a threat? If it is, then let's keep this going. If it's not a threat, then maybe we should shut this down. Okay, whoa, that was fun, but if it was dangerous, I'm glad we were covered. And the hippocampus is also up here. So if you remember when we talked about the developing brain, we mentioned that the hippocampus also plays a role in stress. Okay. Let's see here. I think this is just a bigger picture of the same thing, a little bit more simplified. This is from a different book, but essentially the same thing. And I'm just going to leave this here, and we'll come back in a little bit.